Hi. I'm Charles. I'm going to present a vulnerability about XORtigate. This is a pre-authentication remote code execution bug that my team and I found early this year for a red team assessment. And so I'm going to describe mostly the exploitation phase of the vulnerability. However, I will still talk a little bit about the context and the environment. And finally, I will conclude with a few words regarding how you can fingerprint the firmware or stuff like this, because I know a lot of people are interested in this. Sadly, I only have 30 minutes, so we are going to need to go really, really fast early on to have some more time for the bug and the exploitation. So regarding the context first, as I said, red team audit, basically no attack surface, only a FortiGate. So yeah, we had to attack it. We had a few months, I think, for this audit, so we had quite some time, and we are pretty confident that we were going to find a bug because, honestly, there are lots of bugs on this software. So first step is getting the appliance. The idea is just to connect to the Fortinet website and get a VM for demo license. I think the license lasts for 2 months or something, so that's enough to find a bug and exploit it. The architecture I chose is Intel 64, obviously, and I was ready to go. And the first step is getting a root shell to be able to debug easily. And we were actually quite lucky because when the system boots, it will extract the kernel from an archive which is called rootfs.tgz into slash. And then it will also decompress datafs.tgz into slash data. The rootfs.tgz archive is signed, so you can't modify it easily. I didn't check if the signature is properly verified or not, but I assume it was. I mean, it's not always the case with Fortinet, but... And so I had to focus on datafs.tgz. And the thing is, there's actually a path traversal while the archive is going to be decompressed. So you can just insert files such as bin/ssh, and they will get decompressed into the rootfs. And so that's a very easy way to get a root shell. You just edit one file in the fs, and when it boots, it will overwrite the SSH binary. And when then you use the SSH binary, for instance, by issuing the execute SSH command, it will actually fire your binary instead. You get a root shell really easily. So now you can reverse, and there's actually one big binary, which is called bin init, and it does literally everything. It's 65 megabytes big, so it's huge, but there are no symbols. So this is a little bit annoying, but you can actually get quite a few symbols from the log messages, which helps to get started. In any case, as I said before, the attack surface for us was pretty small because we wanted to target the internet-facing interface that allows users to authenticate. So that's the only interface that we could reach. And we were interested only in pre-authentication bugs because we didn't have anything, we didn't have credentials or any way to get them. So it was only pre-auth bugs. And we realized that the HTTP server was based on a very old Apache, but they modified it a lot. So we couldn't match like the original structures from Apache 1 with the code. And so we had to basically reverse from scratch, but we actually found the bug like pretty fast. I think after 1 week or so, my colleague actually managed to find a really good bug. And so I'm going to talk about this bug. So the bug happens when you go on the remote/hostcheck-validate page. I have no idea what this page does, but it contains an HTTP parameter, which is called enc. And this parameter is encrypted. We don't really care about what it contains. We don't really care about what it does. Again, we are really only interested in the decryption process because this is where the bug lies. So the enc parameter is actually made of 3 parts: a seed, a size, and a ciphertext. Everything is sent as ASCII hexadecimal. So when you want to send 1 byte, you actually send 2 XCHARs, right? And so the seed is 4 bytes long, the size 2 bytes long, and the ciphertext has varying size. Evidently, since it's in XCHARs, the seed is 4 bytes long, but you send 8 XCHARs to send it. The same for the size, which is 4 XCHARs, etc., etc. And so the 2 last parts, the size and the ciphertext, are actually encrypted. And they are encrypted by being XORed with a keystream that is generated from the seed. Okay, so they take the seed, they generate a key stream, and then they XOR the ciphertext and the size with the key stream to decrypt them. And so how is the key stream generated? Well, it's made from 3 parts as well to get a key. The first part is a salt, which is given by the server. It changes when the process reboots, but it's easily obtainable. It's not hidden in any way. You can just issue a GET request to some page, and it will give you the salt. So it's not hidden. You can just have it, right? Then the seed is chosen by us, right? It's sent as a part of the enc parameter. And then there is some constant, which for some reason is GCC is the new compiler collection. And you take all these parts together, and you get a key. And then you want to generate a key stream, and to do this, you will take the key and compute the MD5 of it, and you will get 16 bytes. This is S0, the first 16 bytes of the key stream. And then if you want 16 more bytes, you compute the MD5 of S0, so S1 is equal to MD5 of S0. And if you need 16 more bytes, you compute the MD5 of S1, etc., etc., etc. So the key stream is basically an MD5 of an MD5 of an MD5 of an MD5, etc., etc., etc. So now, let's have a look at the decryption logic. As I said, the payload is sent as ASCII X, so the first step is converting it into bytes. So a buffer of size n divided by 2 plus 1 is allocated, and then the payload is decoded from ASCII X to bytes. There are no bugs there. Then the size needs to be decrypted. As I said, it's encrypted, so it consists of 2 bytes, so you XOR them, those 2 bytes, sorry, with the first 2 bytes of the key stream. And then you get the decrypted size. And then what you need to do is to check that the size doesn't exceed the size of the buffer. You are checking for overflows. And what you do is simply compare the size with the size of the payload minus 6, which kind of makes sense because the seed is 4 bytes long and the size is 2 bytes long. So the remaining part is actually n minus 6, right? And then using the size, you know how many bytes you need to decrypt. So for instance, if the user sends a size of 20, you know that you are going to need to XOR 20 bytes of the ciphertext with the key stream. And at the end, you add the null bytes to avoid leaks. So that's why you allocate n divided by 2 plus 1 bytes so that you can store the final null byte. So you may have spotted the bug. The given size, so the size sent by the user, is actually the size of the buffer in bytes, and it's being compared to the size of the payload, which is in ASCII X. So the size can be actually twice as big as it should be. And that means that the decryption process can go past the buffer, and the resulting problem is that we can XOR adjacent memory with a key stream. So that's why we named the vulnerability XORtigate. It's because we don't have an overflow where we overwrite bytes. We have XOR overflow where we can actually XOR bytes with some key stream. So let's have a look at the primitive. We can allocate a buffer of size X on the heap. Then we can XOR Y bytes past that buffer with a key stream. And the key stream is a bunch of MD5 values, of which the first has been computed from a key which is partially controlled by us. And again, last byte is set to nil. So let's see what happens if we trigger the bug. We are sending a size that is bigger than the size of the buffer. So in blue, you have the original memory before the decryption. In yellow, the key stream. And then after this, the XOR operation resultant. So as you can see, the end of the decryption is after the end of the buffer in the memory because we have sent a size which is bigger than the size of the buffer. And so when you decrypt, you actually end up decrypting legit memory, but then decrypting memory that is not yours. And so you can actually realize that we are modifying memory that we don't really control. And after this, a null byte is appended, as I've said. So the vulnerability would actually be really, really good if we control the key stream. However, the key stream is actually an MD5, an MD5, an MD5, as I said. And you have to realize that we are not dealing with 1 or 2 MD5s. We are dealing with hundreds of MD5s. So we can't really expect to control as many bytes as we want in the key stream. We might expect to control a few of them by brute forcing the seed, but that's it. So what we get right now with the primitive is garbled memory and a null byte. So this is pretty bad. However, the XOR operation has very nice properties, right? There's the self-inverse property, where if you XOR B with B, you actually get 0, and the identity, where anything XOR 0 is actually equal to the original value. So what happens if we apply the bug twice? Well, let's try doing it. So let's try doing it first with an overflow, XOR overflow of 5,000 bytes. So again, original memory being XORed with the key stream. So the first byte here is 98. It gets XORed with 91, and it becomes 09. The same happens for the next one. FD XORed with 7B becomes 96, etc., etc., etc. And so you end up having memory that has been XORed with a key stream, and then again, a final null byte. So what do we have now? As I said, as I promised, on the left, carbon memory, then a null byte, and then on the right, completely unchanged memory. So it's not really exploitable like this. It looks like a pretty bad bug. But let's try doing it again from the same address with the same seed, so exactly the same key stream, but this time with one more byte of overflow. So instead of overflowing for 5,000 bytes, we overflow with 5,001 bytes. So again, we're going to do it step by step. So 9 gets XORed with 91, and it becomes 98. Makes sense. The original memory was 98. We XOR it twice with the same byte from the same key stream, so 91, so it becomes its original value again. We do it again for FD, it becomes FD again. Same for the next bytes. The only difference is that when we reach the end of the first XOR overflow, we have set the byte to null. So when we XOR it with the byte of the key stream, because we have an overflow that is a little bigger, we will actually have the byte of the key stream that is inserted, because anything XORed with 0 is the value itself. And so again, afterwards, we have the final null byte, as usual. So what do we have now? We can see that the memory in blue and in purple is actually almost the same, except for one byte that has been replaced, the byte at offset 5,000, and a null byte on the right. And the good thing about this is that we can actually control the byte which has value 50 here, because we control the seeds. And this is only a 1 byte constraint on the whole key generation process. So what we can do is simply try and brute force a seed such that the byte at offset 5,000 has value OX50. That's it. So we need to compute a few MD5s. It takes a few milliseconds. And then we get a valid seed that will give us the byte that we want. We don't care at all about the other bytes. And so now we have a very good primitive, because we can allocate a buffer of size X on the heap. We can convert any bytes at offset Y to an arbitrary value without changing the rest. And the only downside, again, is that we get a null byte on the right of that byte. But that's it. And so the impact is huge, because if you think about an overflow, if you want to overwrite something that is like 40 bytes away, you overwrite everything in between. But with this bug, you can actually pick the parts in the memory that you want to overwrite without changing anything else. So that's actually a bug that is way better than an overflow. So now I have a really, really good primitive. So I'm ready to exploit in the lab. So in 2019, the DevCore team that you've seen twice over the last days actually used the buff to overwrite a structure which is named SSL. And the structure is managed by the OpenSSL library. It's the main structure of the OpenSSL library. And it will control every socket that is SSL wrapped. So if you connect with an SSL socket to the FortiGate instance, an SSL structure will get instantiated. So during the SSL handshake, the SSL structure will be used to call a function pointer, which is called handshake func. And so the idea was that they could actually use ROP to exploit. They just overwrite handshake func, do a ROP, and get code execution. And we're actually going to do this as well. So we are going to overwrite SSL handshake func without altering the rest of the structure, because we have a very good primitive. Then we trigger the SSL handshake, and we are done. We have code execution. The only requirement for this is that the primitive requires us to allocate twice exactly at the same spot. And we're going to see that it might be a problem. The SSL structure for Intel 64 bits is of size around 2000, so it gets allocated in chunks of size 2000. And the allocator is gmalloc. I didn't know this allocator at all, and there is a framework called Shadow, And I tried to use it for like a few hours, and then I just rage quit. I think other people in the room didn't manage to use it, so it's not only me. The last commit was 6 years ago, so that might be why, but also you need a lot of configuration and stuff. So I was like, yeah, well, fuck it. I'm going to try and do it by myself. And I learned to try and error. And I got 3 rules from this. The first rule is that you can, if you spam allocations, at some point you will get contiguous allocations. It's pretty standard, but still it needs to be set. Then there is some kind of LIFO cache for same size allocs. So if you free a chunk of size 50, the next allocation of size 50 is going to be at the same address, right? So it's basically the same as Tcache for ptmalloc. And also, there is absolutely no metadata in between chunks. So that's really useful for us because we can safely overflow from one chunk to the other without risking to break anything. So now we have a very naive heap strategy in our heads, which is create lots of sockets, SSL wrap them, and we're going to get a lot of SSL structures in memory that are contiguous. But that's not the case, because when you create an SSL socket, you actually get a lot of allocations, and this messes up the heap. So we need to do better. And so every time I attack an HTTP server, like Apache or Nginx, I use postdata to set up the heap, because this is actually the best thing that you can do. You can get arbitrary number of allocations by sending any number of parameters that you want. You have an arbitrary size for your allocations because you control the size of the parameters. And you also have arbitrary contents because you control the value of your parameters. So that gives you a very, very easy way to get the heap like you want it before exploiting. And so we have a real heap setup strategy now, which is that we create and free contiguous chunks of size 2000 using the postdata. Then we create and wrap a few SSL sockets. And this way, we will actually manage to get contiguous chunks of size 2000. The problem is that I didn't think about the HTTP request buffers. Every time you create a socket, the FortiGate instance expects an HTTP request, and it creates a buffer to store the HTTP request. The problem is that the HTTP request buffer has the same size as the SSL structure. And so you end up in memory with HTTP request SSL, HTTP request SSL, etc., etc., etc. And the problem is that we want to overflow into SSL. So we want to get rid of the HTTP request buffer. Luckily, we can do it very easily, because if we send a huge request, the buffer will actually get reallocated, and so it will leave the original chunk free. And this free chunk is actually the place that we want to be in. So we reallocate the HTTP request, and then we use the free chunk to trigger our primitive repeatedly. And that means that we can overwrite uncheck func, and using ROP, we get code execution. Again, we have, there's one thing also. It is that the uncheck func is called when you actually negotiate the SSL session. And since we have sent an HTTP request, that means that we have already negotiated the SSL session. And the beauty of the bug is that we can edit anything in the structure without breaking anything. So what we can do is simply override flags in the SSL structures. Those flags are way after the uncheck func, and just make it think that the uncheck has not been done. So you send a request to reallocate, and then you make it think that the uncheck has not been done, and when you send anything, it will think that it is the uncheck again, and it will trigger uncheck func. But then we have another problem. We need to trigger the bug lots of time. Like even for one primitive, we need to trigger the bug twice. And we absolutely need those bugs, every single bug, to be exactly from the same address, otherwise we get a crash. And a crash will actually disconnect everybody, so you will probably get caught, or at least they will get suspicious, right? And so my first exploit, which was the one I just described, was not so stealth, and I wanted to get something better. And what I did was try and use the heap more effectively and discover a chunk size that is never used, or basically never used. And by trial and error again, I found C00. There was a chunk size that was basically never used. And then I built the heaps such that I have chunk size of C00 right before chunks of size OX2000. And the idea is that now my chunk will never get stolen, so I can just continuously overflow from this chunk size to the SSL structure without breaking anything. But this requires me to understand the heap like way more precisely, and it's really, really hard to set up. So it took me quite a bit of time, but after a while I actually managed to do so, so I was pretty happy with it, and I was like, okay, I've got 2 exploits, including one that should actually work in real conditions, so I'm ready to try IRL, right? And, well, this is when I realized that there were actually 100 builds per version, even more, I think. And so my exploits were for Intel 64 bits, but the target was neither Intel, neither 64 bits. It was actually ARM32. And so, yeah, I'm actually stupid. That's the second time I do this, but yeah. And so I had 2 kinds of problems. First, the fact that it's 32 bits. So the relations between the size of the structures is completely different. For instance, the SSL structure, which is mostly made of pointers, is divided by 2. So it was 2,000, it becomes 1,000. The request buffer is a char buffer, so its size doesn't change. And so the relation between the 2 doesn't work anymore. The C0 chunks that I was using to overflow safely are very much in use now, and I couldn't find any chunk size that was not in use. So my previous 2 exploits were actually completely useless. And also, I had CPU problems where I wasn't able to emulate the ARM firmware. You might be able to do it, but I wasn't. I'm really a noob with this. And I didn't want to buy the appliance. So, yeah. I tried to do a meet me halfway approach where I create an exploit for Intel 32 bits, where the structure size is actually consistent with ARM32. And then I guesstimate the ARM warp chain, emulate it through QEMU. Then I put the 2 together, and I hope for the best, and we'll see if it works, right? And so luckily for me, the Intel 32 bits exploit was pretty similar with the one for Intel 64 bits, because even though the HTTP request buffers don't have the same size as an SSL structure, the HTTP response buffer now have the same size as an SSL structure. And so my heap layout is basically the same. I get an HTTP response followed by an SSL chunk, an HTTP response followed by an SSL chunk, etc., etc., etc. And I just need to find some kind of a text injection bug where I send an HTTP request of which the content is reflected in the HTTP response. And so the HTTP response buffer gets reallocated, and I get a free chunk right in front of the SSL buffer. So that's what I did. And that gave me an exploit that was similar with my first exploit. So it worked, but only if you are alone on the server. Then I needed to take care of the ROP. I knew that the register S7 was controlled by us. So I just did a very small pivot, and I started Node.js because there is no shell on the appliance. And then I emulated it through QEMU, and it seemed to work, right? So I was ready to test it, but obviously, really unstable exploit, untested ROP chain, so I can't really afford a crash. So instead of trying to do it during office hours, I just tried to exploit at 3 a.m. when nobody is on the VPN. And that was probably the safest thing that I did in this thing, because it actually worked out. And then I was pretty happy with it, and what I did was simply hook the login procedure so that when anybody connects, I get their credentials in clear text for free, and just wait. And luckily for me, the next day, the RATP, which is the Parisian Public Transportation System, was on strike again. And everybody was working from home, so everybody gave me their credentials, including the 4 domain admins. So in like 4 hours, I think we had any single credential in the enterprise, like except maybe a few, but yeah. So successful red team. So I'm going to show you a little demo because I don't expect you to trust me on this. And I'm going to do it live. So, yeah. Obviously, on the left, you have the interface, my exploits on the top right, and on the bottom, hopefully at some point, a shell. And nope. Just one thing, as you can see, the get UID returns 0, so that means that we are root on the appliance, so we can do anything we want. And I will quickly conclude. So there were quite a lot of affected products, actually. We didn't really expect that many products to be affected. I think the ENC parameter was really like a legacy parameter that they kind of forget. I don't think it's used right now, but I might be wrong, so you shouldn't take my word for it. But still, like lots of versions affected. And I have published one of the exploits on GitHub a few days ago. There's the blog post on our website, blog.lexploit.fr. And also there is the advisory from Fortinet. I think we have some time for who we are, because I didn't actually describe our company. We are a French offensive security company based in France, so mainly Paris, Lyon, and Toulouse. We do lots of things, including red teaming, pen test, VR, CTI, and we are recruiting. We have two blogs. One that is more about web research, which is called embryonics.io/blog. And the other one, which is more about, well, all the rest. So it's blog.lexploit.fr. And yeah, that's it for me.